Hello, my name is Mitch. I am working alongside Tyler, Chris, and JY, and we are Car Safety Incorporated. Today we will be presenting automatic cruise control. This is our control system that will automatically drive cars on the road. For this project, we are aiming to design a control system that can monitor the speed of a vehicle ahead of the driver and maintain a safe distance behind them. In our modern age, self-driving cars are becoming much more relevant, and it's important to innovate this technology as quickly as possible to get it out to everybody. Our automatic cruise control system will maintain the distance to the car in front of them and ensure and prevent all accidents on the road. Our performance goals for this project, our first one is our rise time. We hope to make it less than or equal to 7 seconds. Note that our crossover frequency is 0.3 radians per second. Our theoretical time to reach 90% speed, we're hoping to reach 60 miles an hour, and so we want to reach 90% of that in 7 seconds or less. Our second performance goal is our percent overshoot, which we aim to keep below 20%. Notice that our phase margin is greater than or equal to 56 degrees. This will determine how close the vehicle can be to the car in front of them and maintain a safe distance behind them as they accelerate. Our third performance goal is our steady state error. We are going to add an integrator to set this to 0. This will help prevent all accidents and keep our cars safe on the road. Up next, JY will present our physical model of our car.
Hi, my name is JY, and I'm going to present to you our physical setup for the automatic cruise control system. So, we created a free body diagram, and in order to further model a velocity control system, we realized that this was a system meant for both acceleration and deceleration of a car. So the acceleration is nicely modeled because it's a simple correlation between the force of the engine and how fast the car can go. But for the deceleration part, we noticed that we needed to model it using the force of drag because we didn't necessarily include that in our design. So for further analysis, we converted our physical model into a different physical model, a mass damper physical model, where the force of the wind is modeled by a dampener. The engine is an input, to the mass, where the mass is our car, and it has a 1,000 kilogram mass. And the output is the distance or your relative X position as a function of your input. So from this mass dampening model, we know that dampeners and masses can be converted into impedances. So our impedances are modeled as so, and we found that the general transfer function, so the one that's going to give us our performance goals, which is the percent overshoot, the rise time, and the steady state error, we have to find the transfer function in order to be able to get those values. So we notice that our transfer function is 1 over 1,000 s squared plus 0.5 s. Now, these two numbers right here are input into here, and our transfer function is then found to be both dependent on the mass and the mass dampener. So next is Tyler.
And so in order to implement our project and meet the requirements that we were looking for our system, we needed to design some sort of controller. And we set out to design this controller using MATLAB and SISO tools so that we can kind of input our performance requirements and then look at what we need in order to meet that. And so the first thing about our system was, as our transfer function is already type 1, and this is because there's an integrator in both of the terms already. And so this allows us already to have steady state error driven to 0, which was one of our initial performance requirements. And so this allows us to not have to input another integrator into our function for the analysis. And then as you'll see in the following plot, there were no poles in the open right half plane for our root locus. And this indicates that our system has an infinite gain and will be stable at any gain level that it's driven up to, which is a plus for any sort of system. And then, so the first step in our analysis was we started with a proportional controller, and this allowed us to only tune the gain for the system. And when you're working with a proportional controller, there's a trade-off between the phase margin and the percent overshoot values when you're adjusting that for the phase margin and the crossover frequency. And so you're only able to make one better and the other one gets worse depending on which way you tune the proportional controller value. And so in order to correct this, we needed to develop a different type of controller. And so we added a 0 into our system on the Bodie plot, and that allowed us then to create a proportional derivative controller, which then allowed us to both bring our phase margin and our crossover frequency into the ranges that we were looking for. And then you'll see on the plots here what the values are.
Yeah, so I'm Chris, and here are our Bodie plots for our proportional controller. And essentially a proportional controller is just our basic transfer function with our constant on top tuned. So as you can see, our phase margin here is only 0.1 degrees and our crossover frequency is 0.36. Comparing these to our actual performance goals, our crossover frequency is nearly there, but our phase margin is off by almost 45 degrees, which is why we had to add a 0 to the proportional controller to make a proportional derivative controller. And next. And so this is just a basic root locus diagram of our system. As you can see, our two original poles from our original transfer function, plus this added 0, give us this overall root locus diagram for our proportional derivative controller. And then moving on from that, these are our Bodie plots for a proportional derivative controller. As you can see, our phase margin is now 46.2 degrees, and our crossover frequency is 0.38. And these are finely tuned after we found our controller value of 100 plus 270S. So with our phase margin of 46.2 and our crossover frequency of 0.38, we reach our rise time of 5.78, which is within our performance goal, and our percent overshoot of 19.8, which is also within our performance goal. So I'm gonna pass it back over to Tyler, and actually one more second. This is just the basic step response of our system, and as you can see, it rises, there's some overshoot, and it settles back down to the speed. All right, now I'm gonna pass it over to Tyler, he's gonna talk about the analysis.
And then, so for the final part of our analysis, it was kind of we needed to perform a sort of reality check on our system. As we know from other projects and just intuition, there are limits to what physical capabilities are of different systems that are created. You know, whether it's a limit for an output torque of a motor or the voltage a car battery can deliver, there is a limit. So we needed to look at our system and examine it and make sure and discover whether it is applicable and we can create it, or if it's at this point an unattainable system and further work will need to be done to refine it. And so for our final controller, we ended up with, we didn't have to add an integrator, but we had a 0, and this allowed us to meet our requirements. And as you can see, this is what our final transfer function with the controller, with the PD controller put in looks like. And we have an infinite gain margin, so theoretically we're able to crank up the gain on our system to an infinite level, which for our system with the self-driving car would correspond to motor power. And so this is the value we need to check and ensure that it falls within realistic standards. If not, you know, it's very easy to design a car that if you increase the distance it needs to travel, it just multiplies the power for the motor by that, but you reach a certain point where motor power is then unattainable. And so for that part of the analysis, we wanted to look at this block diagram down here. So this was the one that we used for the tuning of our system. Here's the controller and here's the plant transfer function. And this system takes the input and then the output is the position of the car relative to the cars in front of it. And so this allows us to tune our system for the controller to meet our system requirements with regards to location of the car and where it is on the road. But then in order to kind of perform this reality check and check the output of our motor, we need to use this new block diagram. And so this is with our controller here and the plant transfer function in the feedback loop. And then what this allows us to do is look at the force that is being output by the motor. And so that's different, and this is a more applicable value and allows us to kind of perform that, you know, does this work on the system? And then for that, we generated another plot for the system. Okay, so moving on from this block diagram, we have over here the step response that was inputted into that system to monitor the force output of the motor. And as we can see here, it behaves much in the same way as our initial overall system. It goes above our value and then has some overshoot and then settles in. So at least to us, what this indicates, we think, is that our motor isn't using an infinite amount of power. We're not totally sure on this. This analysis would still need some further work because we aren't fully able to understand this, and we would like to maybe add in some different, like a ramp response, which would be more realistic and try to figure that out. But we had some issues implementing that in MATLAB and SISO tools. But at least the conclusion that we draw from this is, since we do see the step response for the system monitoring the force output of the motor settle into a final value, we do feel that that our system does settle into a certain amount of power, and that changing the gain on the controller won't just jump this power up to infinity. So overall, we feel we've designed a fairly decent system that meets all our system requirements, but we would like to do a little bit of further analysis with some more advanced tools into monitoring the force output of the motor, just to make sure that we do have a real world system. But overall, we feel like we were able to design a controller that allowed our transfer function to meet all of our performance requirements, and that our project and controller overall meet all the goals that we set out to accomplish in the beginning of our project. So thank you for your time.